In this lecture, we'll cover the concept of time dilation and we'll use the Lorentz transformation for deriving the relationship for the time dilation. Let this be a frame which is stationary and let there be another reference, another frame which is moving with a velocity v. Let this frame be s dash. Let there be an observer in frame S dash and observer in frame S. Let there be an event which could be a pulse being generated, being reflected, coming back and being recorded. So two events at same location at two different times. So same location but two events, and there will be a time elapse delta t0 between these events, and since we are measuring at the same location, so we call it as a real time, which the two events could be a pulse being generated, being reflected by the mirror, and pulse coming back. Now, for an observer who is in the stationary frame, what time does he measure for these two events which are taking place in the reference frame S dash, which is moving? Now, to find that, we have to recall the relationships between the x, y, z and time coordinates for the two reference frame. We know that x dash can be written as k times x minus vt, where k is 1 upon under root 1 minus v square upon c square. C is the speed of light. Y dash is written as y because there is no movement along y and z axis, and z dash is z, so there is no velocity in z or in y direction of the S dash frame, and t dash is written as k times t minus vx upon c square. We can also write this relationship as x in terms of x dash. X will be k times x dash plus vt dash. Y will be y dash, z will be z dash for the same reason as here, and t would be k t dash plus v x dash upon c square. Now we have to use these transformations and we have to decide which one relationship is relevant in our case. Now we have a situation where the reference frame S dash is moving and we want to measure time at the same location in that reference frame. So when we use this transformation, we use the S dash reference frame having t dash and x dash both. X dash is the location and t dash is the time. So we use this relationship where we know t dash and x dash, and we have to find the time t that is in the fixed reference frame. So t is k t dash plus v x dash upon c square, or delta t would be equal to k delta t dash plus v delta x dash upon c square. We know that in this moving frame the events happened at the same location, so delta x dash is 0. So delta x dash happens to be 0, so delta t is equal to k times delta t dash. Delta t dash is the real time. Delta t0 means time which is measured at the same location where the events have happened. Means events are happening at a given location x dash, and there we are measuring the time intervening between the two events. Unlike the time being measured by this observer where the events are happening at two different locations, because this frame is moving where the events are happening. So between first and second event there is a location difference as far as this reference frame is concerned, but for these two events in the moving reference frame there is no difference in the location. Delta x dash is 0, so when it is measured at the same location we call it as a real time. Now value of k we know, so delta t is delta t0 upon under root 1 minus v square upon c square. Because of this factor of 1 upon under root 1 minus v square upon c square, which we call as k here, or we can also call it gamma, this factor is greater than 1. So delta t is greater than delta t0. This is what is the time dilation. So the observer in the rest frame will measure a greater time between these two events as compared to the time which is measured by the observer in the moving frame, and this is what is called the time dilation.